For years, the phrase quantum advantage has been thrown around so loosely in so many press releases, conference keynotes, and defense contractor pitch decks that it basically stopped meaning anything at all to E-Left trying to figure out whether they're looking at a genuine strategic threat or just another overhyped press release dressed up. In impressive-sounding physics jargon, that confusion just got a lot harder to hide behind because on July 9th, 2026, a team of researchers from Caltech, MIT, and Google Quantum AI published something that quietly changed the entire conversation. Not a new quantum chip, not a flashy new record, a mathematical definition rigorous enough to, finally, separate real quantum advantage from wishful thinking, and the implications for how America evaluates its quantum defense strategy are honestly bigger than almost anyone outside the physics community has fully grasped yet. Let's start with why this problem actually exists in the first place, because you genuinely need to understand the mess before you can properly appreciate what just got cleaned up so carefully. Quantum computers, in theory, can solve certain kinds of problems dramatically faster than any classical computer ever could. That basic premise is what's driven billions of dollars in government and private investment over the past decade. The entire foundation of the strategic competition with China we've talked about before, the entire justification for the Pentagon's aggressive push toward post-quantum cryptography. But here's the uncomfortable truth that researchers in the field have quietly wrestled with for years. Proving that a quantum computer genuinely outperforms the best possible classical approach to a given problem is astonishingly difficult. And the history of this field is absolutely littered with claimed advantages that later turned out to be nothing of the sort. Here's a perfect recent example of exactly that trap, and it comes from Caltech itself, which makes it a genuinely useful illustration of the whole problem. For years, a specific chemistry calculation involving something called the FeMo cofactor, a complex molecular structure found in nitrogen-fixing bacteria, was treated as a flagship target for quantum advantage in chemistry. A problem so computationally hard that classical computers were assumed to be fundamentally incapable of solving it accurately. Then, a Caltech research team led by Garnet Chan used cleverly optimized classical tensor network methods and simulated that exact same problem to full chemical accuracy, without any quantum computer at all. The lesson embedded in that result is genuinely humbling for the entire field. Classical algorithms keep moving the goalposts. Every time quantum researchers point to a problem and say, only a quantum computer can solve this, brilliant classical, computer scientists eventually find a clever workaround, and the supposed quantum advantage quietly evaporates. That pattern has repeated itself often enough that serious researchers have started asking a genuinely uncomfortable question. How do we actually know, with real mathematical confidence, when a quantum advantage is genuine and permanent, rather than just a temporary gap that better classical algorithms will eventually close? That is precisely the question this new Caltech, MIT, and Google Quantum AI paper set out to answer. And the team behind it is genuinely impressive. Hsinyuan Huang from Caltech, Soonwon Choi from MIT, Jared McLean from Google Quantum AI, and John Preskill, the Caltech physicist famous throughout the field for coining the term NISQ, short for Noisy Intermediate Scale Quantum, a phrase that has shaped how the entire industry talks about the current, still, imperfect generation of quantum hardware. Together, this team built what they call a mathematical framework for evaluating quantum capabilities across 4 distinct domains: computation, learning, sensing, and communication. And at the heart of their framework sit 5 specific properties, which they argue any genuinely ideal quantum advantage needs to satisfy simultaneously: predictability, typicality, robustness, verifiability, and usefulness. Let's actually walk through what each of those 5 words means in practice, because this is where the framework goes from abstract academic theory to something with genuinely serious defense implications. Predictability means researchers can reliably forecast, using solid theoretical grounds, the TA quantum advantage will actually exist for a given problem before ever having to build the hardware and test it empirically. Typicality means the advantage shows up reliably, across a broad range of realistic problem instances, not just one narrow, artificially cherry-picked example, specifically engineered to make quantum computers look good. Robustness means the advantage survives real-world noise and imperfection, the messy, imperfect conditions actual quantum hardware operates under today, rather than only working in some idealized, mathematically perfect scenario that will never exist outside a textbook. Verifiability means an outside observer can actually confirm the quantum computer got the right answer, without needing another, even more powerful quantum computer, just to check the work, which sounds obvious until you realize how many proposed quantum advantage demonstrations completely fail this exact test. And usefulness, the simplest sounding criterion, but arguably the hardest one to satisfy in practice, means the problem being solved actually matters to someone in the real world, rather than being a purely artificial mathematical puzzle constructed specifically to be hard for classical computers and nothing else. Let's go back a few years and revisit exactly how we got to this point of confusion in the first place, because the history here genuinely helps explain why a rigorous framework became so urgently necessary. Back in 2019, Google made global headlines by claiming it had achieved what researchers at the time called quantum supremacy, demonstrating that its Sycamore processor could complete a specific, carefully chosen calculation in roughly 200 seconds, a calculation Google claimed would take the world's most powerful classical supercomputer approximately 10,000 years to replicate. That announcement generated enormous excitement, plenty of breathless media coverage, and no shortage of confident predictions that quantum computing had officially arrived as a genuinely transformative technology. Then, within months, researchers at IBM published a detailed rebuttal, arguing that with sufficiently clever classical engineering, that exact same calculation could actually be completed on a classical supercomputer in a matter of days, not 10,000 years. The supposed decisive quantum advantage suddenly looked a lot less decisive, reduced from an unbridgeable 10,000-year gap down to something closer to an ordinary engineering challenge that classical computing could plausibly still solve, given enough clever optimization. That entire episode, still remembered vividly across the physics community, perfectly illustrates the exact problem this new framework is specifically designed to solve. Google's original claim was not necessarily dishonest or fabricated. It was based on a genuine, carefully measured experimental result. But it lacked the kind of rigorous verifiability and typicality that would have made the claim durable against later, smarter classical rebuttals. The calculation itself was also, by most honest assessments, let's talk about a genuinely striking result that came out of this exact same Caltech research community, one that helps illustrate precisely why a rigorous framework for verifying quantum advantage actually matters in the real world, rather than staying confined to abstract academic debate. A separate but closely related paper, authored by several of the same researchers, alongside collaborators including Dolev Blufstein and Manuel Endres, demonstrated that Shor's algorithm, the famous quantum algorithm capable of breaking widely used encryption systems like RSA, could potentially be executed using as few as 10,000 reconfigurable atomic qubits, built on a neutral atom architecture. That number matters enormously, because it represents a massive, genuinely startling drop from earlier estimates, which had assumed something closer to 20 million qubits would be required to accomplish the exact same cryptographic feat. If that 10,000 qubit estimate holds up under continued scrutiny, it means the wall separating today's quantum hardware from a cryptographically relevant quantum computer, the kind capable of actually breaking encryption protecting sensitive government and military communications, is dramatically shorter and more climbable than most defense planners had previously assumed. Now, here's exactly where the 5 criteria framework becomes so genuinely valuable for actual policymakers trying to make sense of a claim like that. A result, like the 10,000 qubit Shor's algorithm estimate, needs to be rigorously evaluated against predictability. Does solid theory actually support this number, or is it based on optimistic assumptions that might not hold up under real-world conditions? Against typicality, does this approach generalize reliably across different cryptographic targets, or does it only work for one narrow, specifically chosen case? Against robustness, does the approach still function once you account for the real, messy noise and error rates present in actual quantum hardware, rather than the clean, idealized conditions assumed in a theoretical calculation? Against verifiability, can outside researchers actually confirm this claim holds up, rather than simply taking the author's word for it? And against usefulness, well, in this particular case, usefulness is depressingly, obviously satisfied, since breaking RSA encryption protecting nuclear command systems and classified communications is about as consequential and useful a target as quantum computing could possibly have. This is exactly the kind of rigorous evaluation the Pentagon, the National Security Agency, and every serious defense policy analyst desperately needs to be applying to every single quantum threat claim floating around right now, whether it originates from American research labs, from China's state media showcasing its own quantum breakthroughs, or from private companies pitching lucrative new defense contracts built around impressive sounding but ultimately unproven quantum capabilities. Before this framework existed, in any kind of rigorous, widely accepted form, defense planners were essentially forced to rely on reputation, general scientific consensus, and educated guesswork to separate genuinely serious quantum threats from overhyped marketing claims. Now, for the first time, there's an actual mathematically grounded checklist available. Let's talk about why this genuinely matters for defense budgeting specifically, because the financial stakes here are honestly enormous, and they connect directly back to stories we've already covered. The federal government has been pouring enormous, genuinely staggering sums of money into quantum research and quantum-adjacent companies. The National Quantum Initiative has been reauthorized with $1.8 billion in fresh federal funding running from 2025 through 2029. The Department of Energy operates 5 dedicated quantum research centers backed by $625 million in committed funding. The White House has separately announced backing for 9 specific quantum companies worth roughly $2 billion in direct incentives. Every single one of those enormous funding decisions ultimately depends on some underlying assumption about which quantum technologies and which specific companies actually represent genuine, durable advantage, versus which ones are simply riding an impressive-sounding hype wave that could evaporate the moment a clever classical algorithm exactly like the one that dismantled that Famo cofactor chemistry benchmark comes along and closes the gap entirely. Without a rigorous framework like this one, government funding decisions risk becoming a genuinely expensive popularity contest, rewarding whichever company or research-sounding press release, rather than whichever one is actually building something with real, lasting, verifiable strategic value. With a framework like this one, at least in theory, government evaluators finally have concrete, defensible criteria they can actually apply, asking hard, specific questions instead of simply trusting confident-sounding claims at face value. Is this advantage predictable from solid theory, or just an empirical surprise nobody fully understands yet? Does it hold up across a genuinely typical range of realistic problems, or only in one carefully chosen, favorable case? Does it survive contact with real, messy, noisy hardware? Or does it only work inside a clean, theoretical simulation? Can somebody outside the original research team actually verify the result independently? And critically, does solving this particular problem actually matter to anyone in the real world, whether that's cryptographers defending nuclear command systems, chemists designing new materials, or intelligence analysts trying to process massive amounts of classical data more efficiently than ever before? Let's bring China back into this conversation directly, because applying this new framework to Beijing's own quantum claims specifically is arguably one of the single most valuable practical uses. This research offers American defense planners right now. We've talked before about China's aggressive public showcasing of quantum sensing breakthroughs, drone-mounted detection, devices, submarine hunting gravimeters, stealth aircraft targeting radar systems, all presented with considerable fanfare through state media and official military channels. Applying the 5 criteria framework to those specific claims yields a genuinely useful, more measured picture than either uncritical alarm or dismissive skepticism would provide on their own. Predictability: does solid underlying quantum sensing theory actually support the specific detection ranges and sensitivities China claims? Typicality: do these demonstrated capabilities generalize reliably across different operational conditions, weather, depth, distance, or do they only function under one narrow, carefully staged demonstration scenario? Robustness: do these sensing systems maintain their claimed performance under real-world battlefield noise and interference, rather than the clean, controlled conditions of a laboratory or a scripted state media demonstration? Verifiability: can independent outside observers actually confirm these capabilities function as claimed, or must the world simply take Beijing's word for it? And usefulness: well, submarine detection and stealth aircraft tracking clearly satisfy usefulness in the most consequential possible sense, assuming the first 4 criteria genuinely hold up under closer scrutiny. Hindsight using the 5 criteria laid out in this new framework. Google's 2019 announcement clearly satisfied robustness and, arguably, verifiability reasonably well, but it stumbled badly on typicality and usefulness. Exactly the kind of nuanced, mixed picture that a rigorous 5-part. This history matters enormously for defense policy specifically, because it establishes a clear, well-documented pattern. Confident, enormous public and political excitement, and repeatedly turned out to be considerably less decisive than their initial framing suggested, once the broader scientific community had time to scrutinize them carefully. If the Pentagon and other defense agencies had been making major strategic decisions purely based on headline-level reporting about quantum breakthroughs over the past several years, without any rigorous underlying framework for evaluation, they would have almost certainly overreacted to some genuinely overstated claims, while potentially underreacting to other, quieter, but more durable developments that never generated the same kind of dramatic media attention in the first place. Here's the part where all of this stops being an interesting academic exercise and starts becoming genuinely important for how the United States actually thinks about quantum threats and quantum investments going forward. Think back to every single quantum-related defense story we've discussed recently, the aggressive post-quantum cryptography mandates, the executive orders protecting quantum research from foreign intelligence collection, the deep anxiety inside the Pentagon about China's quantum sensing capabilities, potentially threatening submarine detection and nuclear deterrence itself. Every single one of those stories ultimately rests on some underlying claim about quantum advantage, some assertion that a quantum system can do something meaningfully better than classical alternatives. And until now, there has been no rigorous, broadly agreed upon standard for actually evaluating whether those claims are genuinely solid or dangerously overstated. If you're finding this breakdown genuinely useful, go ahead and hit subscribe now, because we're about to walk through a real concrete example of exactly why this framework matters so much, and it connects directly back to one of the most consequential quantum threats facing American national security today. Let's talk about a genuinely striking result that came out of this exact same Caltech research community, one that helps illustrate precisely why a rigorous framework for verifying quantum advantage actually matters in the real world, rather than staying confined to abstract academic debate. A separate but closely related paper, authored by several of the same researchers alongside collaborators, including Dolev Bluvstein and Manuel Endres, demonstrated that Shor's algorithm, the famous quantum algorithm capable of breaking widely used encryption systems like RSA, could potentially be executed using as few as 10,000 reconfigurable atomic qubits, built on a neutral atom architecture. That number matters enormously because it represents a massive, genuinely startling drop from earlier estimates, which had assumed something closer to 20 million qubits would be required to accomplish the exact same cryptographic feat. If that 10,000 qubit estimate holds up under continued scrutiny, it means the wall separating today's quantum hardware from a cryptographically relevant quantum computer, the kind capable of actually breaking encryption protecting sensitive government and military communications, is dramatically shorter and more climbable than most defense planners had previously assumed. Now, here's exactly where the 5 criteria framework becomes so genuinely valuable for actual policymakers trying to make sense of a claim like that. A result, like the 10,000 qubit Shor's algorithm estimate, needs to be rigorously evaluated against predictability. Does solid theory actually support this number, or is it based on optimistic assumptions that might not hold up under real-world conditions? Against typicality, does this approach generalize reliably across different cryptographic targets, or does it only work for one narrow, specifically chosen case? Against robustness, does the approach still function? Once you account for the real, messy noise and error rates present in actual quantum hardware, rather than the clean, idealized conditions assumed in a theoretical calculation. Against verifiability, can outside researchers actually confirm this claim holds up, rather than simply taking the author's word for it? And against usefulness, well, in this particular case, usefulness is depressingly obviously satisfied, since breaking RSA encryption protecting nuclear command systems and classified communications is about as consequential and useful a target as quantum computing could possibly have. This is exactly the kind of rigorous evaluation the Pentagon, the National Security Agency, and every serious defense policy analyst desperately needs to be applying to every single quantum threat claim floating around. Right now, whether it originates from American research labs, from China's state media showcasing its own quantum breakthroughs, or from private companies pitching lucrative new defense contracts built around impressive sounding but ultimately unproven quantum capabilities. Before this framework existed in any kind of rigorous, widely accepted form, defense planners were essentially forced to rely on reputation, general scientific consensus, and educated guesswork to separate genuinely serious quantum threats from overhyped marketing claims. Now, for the first time, there's an actual mathematically grounded checklist available. Let's talk about why this genuinely matters for defense budgeting specifically, because the financial stakes here are honestly enormous, and they connect directly back to stories we've already covered. The federal government has been pouring enormous, genuinely staggering sums of money into quantum research and quantum-adjacent companies. The National Quantum Initiative has been reauthorized with $1.8 billion in fresh federal funding running from 2025 through 2029. The Department of Energy operates 5 dedicated quantum research centers backed by $625 million in committed funding. The White House has separately announced backing for 9 specific quantum companies, worth roughly $2 billion in direct incentives. Every single one of those enormous funding decisions ultimately depends on some underlying assumption about which quantum technologies and which specific companies actually represent genuine, durable advantage, versus which ones are simply riding an impressive-sounding hype wave that could evaporate the moment a clever classical algorithm exactly like the one that dismantled that FEMO cofactor chemistry benchmark comes along and closes the gap entirely. Microsoft has unveiled something called Majorana 1, a proof-of-concept device built around an entirely different topological approach to qubits, one that theoretically offers inherent error protection that could eventually require far fewer physical qubits per reliable logical qubit than competing architectures. And Caltech researchers have assembled the largest neutral atom qubit array built to date, reaching 6,100 qubits, using precisely controlled laser beams to trap and manipulate individual atoms suspended in a vacuum chamber. That neutral atom approach deserves special attention here because it connects directly back to the 10,000 qubit Shor's algorithm estimate we discussed earlier. Neutral atom architectures have emerged as a particularly promising path, specifically because they offer a genuinely appealing combination of scalability and reconfigurability, with the ability to rearrange large numbers of individual atoms into different computational configurations relatively quickly. Google has apparently recognized this potential seriously enough to establish an entirely new neutral atom research lab in Boulder, Colorado, deliberately choosing that location over expanding its existing already established facilities in Seattle or Los Angeles, specifically because Boulder sits close to JILA and the National Institute of Standards and Technology, giving Google direct access to a concentrated community of leading atomic physics researchers that has historically produced many of the field's most important breakthroughs. There's also a genuinely important structural challenge quietly shaping this entire landscape that rarely makes it into mainstream coverage, and it deserves mention here because it directly affects how quickly any of these theoretical frameworks and hardware advances can actually translate into real deployed defense capability. According to a 2026 industry report from the Quantum Economic Development Consortium, the specialized quantum workforce grew by roughly 14% year over year, a meaningful increase by almost any normal standard. But the total number of organizations actively engaged in quantum-related work also grew by that same roughly 14%, expanding to over 7,400 organizations competing for talent simultaneously. That means demand for genuinely qualified quantum expertise is expanding at least as fast as the available talent pool, if not somewhat faster, creating a persistent structural bottleneck that no amount of government funding alone can instantly solve. Even if the Pentagon fully embraces this NE, the U5 criteria framework, and successfully identifies exactly which quantum capabilities represent genuine, durable, strategic advantage, actually building and deploying those capabilities at meaningful scale still depends on a limited, fiercely competed for pool of specialized human expertise, a constraint that money can meaningfully ease but cannot completely eliminate on any realistic near-term timeline. Let's also talk about the sheer pace of progress happening around error correction. Specifically, because this connects directly to the robustness criterion we discussed earlier, arguably one of the single hardest hurdles standing between today's noisy, imperfect quantum hardware and tomorrow's genuinely fault-tolerant systems. The number of peer-reviewed papers focused specifically on quantum error correction surged dramatically, climbing from just 36 total papers published across all of 2024 to 120 papers published within just the first 10 months of 2025 alone. That kind of explosive growth in a highly specific, technically demanding subfield signals genuine, sustained momentum, rather than a single isolated breakthrough that might quietly fade from attention within a year or two. Multiple major research teams, including groups at IBM, MIT, and Google, have continued reporting meaningful advances specifically in reducing error rates and validating entirely new correction techniques throughout 2026, exactly the kind of steady, incremental, technically rigorous progress that tends to eventually produce genuinely robust, durable quantum advantages, rather than the kind of flashy, headline-grabbing claims that later collapse under closer classical scrutiny. Let's step back and think about the bigger picture here, because this framework arrives at a genuinely important, almost perfectly timed moment in the broader quantum computing landscape. Industry roadmaps across the entire field are converging on a rough timeline right now, with IBM targeting a fault-tolerant quantum system by 2029 and expecting verified quantum advantage to be broadly confirmed by the wider scientific community sometime around the end of 2026. Google's own roadmap aims for a genuinely useful, fully error-corrected quantum computer by 2029 as well, building directly on the results from its Willow chip. Quantinuum's ambitious Apollo program targets full universal fault tolerance by 2030. Every single one of these major roadmaps depends heavily on the exact same underlying question this new framework is specifically designed to help answer. When these companies eventually claim they've achieved a genuine breakthrough, how will anyone outside their own research teams actually know whether that claim is real, durable, and strategically meaningful, versus another example of goalposts quietly shifting once again under closer classical scrutiny? Here's something else worth understanding about the framework itself, something the researchers were refreshingly honest about in their published work. They proved that some quantum advantages are genuinely, mathematically unpredictable using classical resources alone, which sounds like a strange, almost paradoxical thing to prove, but it actually reveals something genuinely important about the current limits of our own understanding. It means there are entire categories of potential quantum advantage that classical theoretical tools simply cannot fully anticipate in advance, discoveries that might only reveal themselves through direct, careful experimentation on actual quantum hardware. For defense planners, that finding cuts in two directions simultaneously and both matter. On one hand, it means some genuinely surprising, strategically significant quantum breakthroughs could emerge with relatively little advanced theoretical warning, precisely the kind of scenario that makes continuous, well-funded quantum research monitoring so strategically important in the first place. On the other hand, it also means extreme caution is warranted before assuming any specific, currently unproven quantum capability is either definitely achievable or definitely impossible, since the honest and mathematically rigorous answer, at least for certain categories of problems, is that we genuinely cannot fully know in advance. If this kind of careful, technically grounded breakdown of how emerging science actually shapes real-world defense policy is exactly the kind of content you want more of, make sure you're subscribed, because we cover exactly this intersection. Cutting-edge research colliding directly with national security stakes on a regular, ongoing basis. Let's bring this all the way back around to the original question, because it deserves a direct, clear answer. After everything we've walked through together, did Caltech and Google genuinely redefine what quantum advantage means for U.S. defense? In the most literal, narrow sense, they redefined what quantum advantage means scientifically, publishing a rigorous mathematical framework in one of physics' most respected journals, Physical Review X, on July 9th, 2026. But the defense implications of that scientific redefinition are genuinely enormous, even though almost nobody outside specialized physics and national security circles has fully connected the dots yet. Every single quantum-related defense decision currently being made, funding allocations worth billions of dollars, urgent post-quantum cryptography deadlines, deep anxiety about China's quantum sensing claims threatening nuclear deterrence, ultimately depends on someone, somewhere, correctly judging whether a given quantum capability represents genuine, durable advantage or overstated temporary hype. For the first time, there's now a rigorous, widely respected, mathematically grounded set of criteria available to make exactly that judgment with real confidence, rather than relying purely on reputation, headlines, and educated guesswork. That matters enormously, because the stakes riding on getting this specific judgment right have honestly never been higher. Pour billions of taxpayer dollars into quantum capabilities that ultimately turn out to be overhyped, and you've wasted resources that could have gone toward genuinely urgent national security priorities elsewhere. Underestimate a quantum capability that turns out to be dangerously real and durable, dismissing it prematurely as mere hype. And you risk being caught genuinely unprepared when an adversary actually deploys it against you in a real crisis. The 5 criteria laid out in this new framework, predictability, typicality, robustness, verifiability, and usefulness, offer something the entire quantum defense conversation has been quietly, desperately missing for years now. A genuinely rigorous, defensible way to separate the two. So the next time you see a dramatic headline claiming some new quantum breakthrough threatens American national security, or alternatively, promises to single-handedly guarantee American technological dominance CE for decades to come, remember these 5 words, and honestly, consider borrowing them yourself for your own everyday skepticism toward impressive-sounding technology claims in general, well beyond just quantum computing alone. Is it predictable? Is it typical? Is it robust? Is it verifiable? And is actually useful? Apply those 5 questions rigorously and consistently, and you'll be doing something that, until just this month, even many trained physicists working directly in the field genuinely struggled to do with real mathematical confidence. You'll be separating the quantum computers that could actually reshape modern warfare, encryption, and nuclear strategy, from the ones that simply make for an impressive, headline-grabbing press release and nothing more durable. Underneath it, and in a field this consequential, that single distinction may end up mattering more than any individual qubit count, funding announcement, or dramatic press conference ever could.